All right, welcome to part 2 of the Go programming language. This is Go Faster. This is an introduction to Go programming for people who already know how to program. So I'm not going over the details on if you've never programmed before. I assume that you know something about programming, that you've programmed in at least one other language and know something about arrays and integers and strings and that sort of thing. So so I'm going to assume that you know all this, and what we're going to be talking about is what makes the Go language distinctive. So in this one, we're going to be covering arrays and slices, which is how Go handles when you have multiple things that you need to manage. So arrays and slices, the underlying data structure for Go is the array. And so arrays in Go are strictly values. So if you assign, so if I have the variable a, and it's got an array in it, and I assign it to b, I now have 2 copies of that array. Okay. So you see here in this code, a gets an array of 5 elements, and note if you put that 5 that's in brackets, that tells it that it's an array, an int, and then the curly braces are the initializer. So I'm creating an initial array of 5 elements of the numbers 1, 2, 3, 4, 5. So you got the brackets and the 5 that says it's an array. The int says that what it's an array of, and the curly braces gives you an initializer for the elements. So we create the array in A, and then we assign that to B. And what that does, that actually physically copies all the values of A into B. So when we modify B, we're only modifying B. And you can see in the results there that you have, when you print A, you get 1, 2, 3, 4, 5. And when you print B, you get 1, 2, 9, 4, 5. So this shows you that these really are separate arrays. So everything in Go dealing with arrays, the arrays are treated as values. And so if you pass an array to a function or pass an array back from a function, you're getting physical copies. Now, that's not the same thing with slices. We'll get into slices in a bit. But for arrays, everything is strictly values and strictly copying. So now arrays, because of this, arrays have a lot of limitations. First of all, they're fixed size. You cannot modify the size of an array. If you pass an array to a function, it has to match sizes. Okay, and we can only assign to other arrays of the same size. Okay, so these are pretty nasty limitations. So in Go, you rarely deal with arrays directly. They're usually used as backing storage for other mechanisms. And the purpose for this is just to make Go very fast. Pretty much a lot of the language choices in Go are either about making the code go really fast, being able to inline the crap out of everything, or making the language simpler for the programmer to understand, or making it more straightforward to think about. So those are usually how the thought works in in Go. So as I said, I almost never use arrays myself in Go code, but usually you have arrays standing in the background anytime you use slices, which a slice is somewhere between a list and an array. It's basically kind of a resizable array. Under the covers, slices basically are they are arrays that are linked to each other. So you basically have a backing storage that has some number of allocated arrays. They can reallocate those arrays to get more space. They could deallocate those arrays when they're done with the space, but basically allows you, the programmer, to have a dynamically sized storage space. And slices are normally what Go programmers deal with. So as I said, a slice is kind of like a resizable array, and they look a lot like arrays syntactically. So all the things that you can do with an array you can do with a slice, but they operate very differently, okay? So when you declare an array, as I said, the brackets tell you how big it is, and then the type. So this is a string array with 10 elements. But when you declare a slice, you don't list how big it is, because a slice is resizable. So it can be any number of sizes. Now this will actually give you an empty slice. And then you can also put initializers on slices. So here we have a declaration of a slice, and then we do an initializer. So it has open bracket, close bracket to represent that as a slice, has the name of the type, which is a string, and then in the braces it has the initializers for the slice. So so the braces designate the initializer, and that's a paradigm that's used all throughout Go. That's true for arrays, it's true for structs, it's true for maps. And so as we get into all those things in later episodes, you'll see that the braces usually indicate that it's going to be static initializers. So to append to a slice, you're basically reassigning the slice. So append basically takes a given slice and adds an element to it. And so what this actually does under the covers is it basically, it doesn't necessarily modify the backing storage. It may create more backing storage, but it basically modifies the header of the slice to point to a bigger set of data. So that's why you have to reassign it. So here you say, if I have a slice called my slice, and I want to append to it, I say my slice equals append my slice, and then the value. So this basically creates a new slice. It's the same data, same backing data, but the slice itself, you can think of a slice as a viewing into an array or a set of arrays that itself looks like an array. So it's kind of like we have these arrays way back in the back, and then the slice is a viewport looking at those arrays. And so when you do it, so I can have multiple slices and they're all taking their own views of that array. And if there's more than, there might actually be more than one array out there. And when I do an append, it might change it might add to the window of what I'm looking at in the original array, or it might allocate a whole second array that I now have a window into both those arrays. So append actually has quite a bit of variance as to what it might be actually doing. So, you know, some examples, let's say that we had a backing storage that had an array with 10 values. Now you really have to deal with this. I'm just trying to tell you what it's like under the covers. So let's say you had a backing storage of an array of 10 values, and but you're only using 5 of them. So your slice would be pointing to the first 5. And so when you did an append, what it would do is simply move where the slice is looking on that array. And you append, you append, you append, you append, and it's simply moving where the slice is looking on the array. And then finally, once you get past the end of the array, well, it's got to allocate a new array. And so now you've got a viewport into multiple arrays. Or maybe sometimes it may just allocate a new bigger array. So you don't really get to look at what's happening under the covers. I'm just trying to give you a feel for what's happening there. And so when you do an append, what it's doing is it's literally, the array in the back is not necessarily changing. It's just giving you a new viewport to it. And so that's why you have to reassign it to the slice, because it has to know what the new viewport is. So, and the slice is technically a value, even though it's a value that has a pointer to the arrays. The slice itself, the viewport is a value. So if I didn't reassign it, it wouldn't change. So to access a slice element, it's just like a normal array access. You just put in square brackets, you put which element you want. Go uses zero-based indexing. So then to get a subslice from an array or a slice, you put in your square brackets, you put the starting index, colon, and then 1 after the last index. So if I want to go through index 3, my last one's a 4. So I'm not 100% sure why they did that, but It's a fairly common convention. So this will get you. There's probably a speed issue behind it. Anyway, this will get you a subslice of an array or a slice. So again, it creates a new viewport into existing backing storage. So here's some more functions. Len gives you the length of a slice. Cap gives you the capacity of the underlying backing storage. Now this isn't a hard cap. It just tells you how much data is being used by your slice. And then this copy command, this is kind of a dangerous command because it doesn't necessarily do what you expect it to do. It copies the contents of a slice, yes, but only if it only copies the smallest number of elements of both destination and source. So if you don't already have a slice, so if you're expecting this to like create all new elements, it actually won't, because if your destination doesn't already have enough elements to hold all of them, like let's say your destination is actually an empty slice. Well, this command actually won't copy all the elements. It'll actually copy nothing because destination is empty. It only copies items for which you already have spaces. So we'll look at later on how to actually do a copy. So you can delete an element from the end of the array. You can delete an element from the beginning of the array. These are just by taking subslices. So you just use the colon syntax to get a slice. If I want to delete one from the that second one was supposed to say beginning of an array. So I want to delete one from the beginning of the array, I just start with index 1 and go to the end. If I want to delete one from the end, I go from index 0 to length minus 1. Because remember, length minus 1 is actually the last index, but the right-hand side actually tells you the one after the one that you're looking for. So that'll actually remove the last element. So slices kind of act like pointers. As I've mentioned, they're kind of windows, they're headers that point to backing storage for their contents. So unlike arrays, if I pass a slice to a function and I modify it, especially by setting values, then it will modify the original slice as well. But if I change the slice size or do other sort of meta changes like subslices or appends or anything like that, it may or may not be affected in the original slice. So the actual meta changes won't affect the original slice. So for example, if I get a subslice of a slice, that doesn't change the original slice. If I append to a slice, that doesn't change to the original slice. But it can have strange effects for slices that are dynamically resized. So for example, if I take a subslice and then append to it, well, that might actually overwrite something that was in the original slice. So there's a lot of weird things that can happen. So the reason for this weird backing storage is to make most cases go really fast. So as I said, most of the trade-offs in Go are either for understandability or for speed. And this is one that I feel was made for speed. They're trying to make, actually it's both, because they're trying to make a simplified data structure that's expandable and collapsible, but make it work as fast as humanly possible. So then if you have a slice or an array, one of the common operations is to iterate over all the elements. So let's look at our simple for loop. Go only has one way of iterating, and that's the for loop. So here's a basic iteration that you might see from other C-like languages. Here you have a slice, and so it's a for loop. For idx equals 0, idx is less than the length, idx plus plus, we get the value, and then we print it. Okay, so here is your typical pieces of the for loop. You start out with your initializer, idx colon equals 0. Then you have your comparison, and that tells you whether or not to keep going. And then you have your post loop action, which is usually to increment a counter of some sort. So those are kind of the three common pieces of a for loop. And these are perfectly available in Go. They're separated by semicolons, and that's kind of the basic way. But you actually, the only thing that's actually required in the for loop is the condition. So here's one where you only use the condition. So you actually have the initializer before the loop, you have the condition on the for loop, and then you have the after loop action just appended at the end. But that's not normally how you loop over an array in Go. I just wanted to show that because it's kind of a tie-in from a lot of other languages where you have similar features. And the for loop is important and pretty powerful. If you wanted to have an infinite for loop, you would just say for true, because that's just a conditional that always evaluates true, so it would keep going and going and going. So in Go, to go over arrays and slices, and actually other sorts of objects, use the range keyword. So as I said, there's only one loop in Go, and that's the for loop. But the range keyword allows us to simplify our iteration. So here we have basically the same code as we had before, but instead of iterating through an index that we have to manually set to 0 and then manually increment, we're actually going to use the range operator to do all that for us. So there's the range operator. So range my slice, and that basically says in this for loop, go through each element, set IDX to the index, set value to the value, and then run the loop. And so we don't need any initializers. It automatically iterates over each value. Okay. Now, there's another identifier that's important in Go, and that's the blank identifier. Because Go is very picky about unused variables. In fact, you aren't allowed to have an unused variable in Go. You're also not allowed to have an unused package in Go. Go's trying to keep your code tidy for you by literally failing if you don't do it. So you aren't allowed to have unused variables. So if you have a place where you need an unused variable, so for example, let's say that a function returns multiple values and you don't need the first one, well, if you had to assign that to a variable, if you didn't put a variable, it wouldn't know which one needed to be assigned to. If you put a variable name, then it'd complain because you weren't using the variable. So they have a special identifier called the blank identifier, and it's just an underscore. And so you can use that in cases where you would otherwise need an identifier, but you're not going to use it. And so you're telling Go, I'm not going to use this value. So in the previous example, if we didn't want to use the index and we use the same for loop and we just didn't use the index, it would actually give you an error. So that guy right there would say, no, that's an error. Go would say, you're not using IDX, so this is invalid. So what we'll do is we'll replace IDX with an underscore, and then it works. So it's the same syntax. I have both the index and the value, but the index I'm assigning to the blank identifier, and therefore Go knows that I mean to discard it. So this happens a lot in Go code. You oftentimes have to use the blank identifier. It's a little weird, but you get used to it. So you can see that the IDX is replaced with blank. So here's some examples of array accesses and usages. So to initialize and access a slice, I've got, you can see my initialization there. And then there's a array access. We're setting the first element of A to 3. Then we're going to append, and then we're going to create a new array that has been appended again. Okay, so A, missed that. So A is going to print 3679 because it started out as 367, and then we did an append operation to get 9. And then B, when we did our append, it gets a 10 added on the end. And so remember, these probably are both using the same backing store, but the window is different. Okay, so A is going to stay in that window that has 3679. When we run the B append, that is going to add on a 10 and set the window, but the window, it's not going to set the window for A. They're sharing backing storage, but they're not sharing the window. So, so B gets the new window with the expanded view. So here's how you get so here's showing getting a slice from a slice. So array, so we start with an array, and slice gets a slice of the array, and then the start index, the index plus 1. So this is going to get, so index 1 is 6, index 2 is 7, index 3 is 8, and index 4 tells us to stop, so we're not going to get index 4. So remember the second index is 1 past where we want to go. So then I'm going to get a slice of the slice. So again, this just gives us a new window into the array. So now there's also some shorthands for slices, just to make our lives easier. If I want to grab everything from a given index until the end, I can just do put the index and then a colon, and that'll give me everything into the end. I can also do a colon and then 1 past the last index, and that'll give me everything from the beginning to 1 past, or from the beginning to 1 before the index I specify. So anyway, so those are 2 handy shorthands. And then here's several ways of removing elements, depending on which one you want to remove. So first of all, if I want to remove the last element, I can just do a slice up until the next to last element. If I want to remove the first element, I just do a slice starting at the first index. Now let's say that I want to remove something from the middle. This gets a little trickier. So in this, what we want to do is we want to get a slice and then append everything. So you basically have 2 slices, and you want to append them together. Okay, so we do a slice at the beginning and a slice at the end, and then append them together. So that notice that there's 3 dots at the end after that second slice. What this is doing, the append function actually takes any number of arguments. So I can append any number of things onto my slice. Now, if I did it without the dots, it wouldn't compile, because the slice is supposed to be a slice of ints, and that would basically be telling it, hey, I'm trying to throw an int array onto my slice, and it'd say, no, those are not compatible. But if I do the dots, what that says is it says take the array and treat them as individual elements that are arguments passed to the function. So it'll literally take all of the elements of the slice 3 colon and append them on as function arguments individually. And so that's a handy little tool. Comes into use in several different ways. So anyway, so that's how you remove an element from the middle. You basically create 2 slices and then append with them, and that will remove elements from the middle. So now, as I mentioned, having this backing storage that you don't have a 100% window into can create some issues. So the problems that it creates, first of all, it makes slices a little bit like reference types and a little like value types. So for example, what the value is the window. Okay, so that gets passed every time you assign it. The window gets assigned and moved and passed back and forth by like a value. But part of the window is a pointer to the backing storage. And so that pointer to the backing storage is in fact a pointer, and so it's acting like a reference. Okay, so slices sometimes, but not always, share backing storage. So you should never assume that you do or do not have equivalent backing storage of a slice if you've done appends to it. Now, if you're just doing sub slices, then you can assume that you have the same backing storage. But if you do appends after a slice, then you really don't know if you have the same backing storage or not. So if you need to maintain the same backing storage, only make subslices, don't append. And if you want to guarantee different backing storage, what you want to do is you want to do a full manual copy of the slice. So here's an example of slices sharing memory storage. So here we're going to allocate an initial array and get a slice of it. And then we're going to get a second slice. And then we're going to set the third element of the backing array, of the original array to 3. And what that's going to do is that's going to set that value in all of our slices because they're all just windows into that array. So as I mentioned, if you want to actually have a copy of a slice, you'll need to manually copy it. And so that's going to mean that you're going to need to create a new slice from scratch. Okay, so you need to use some sort of syntax like this to give you just a brand new slice. And then after you have your brand new slice, then you append the elements of the old slice onto your new slice. And so this will give you a new slice that will give you that if you modify it, modify that second index 2 of the original slice, it will not modify our new slice because our new slice uses completely different storage. So to review, arrays are the fundamental multiple value storage primitives in Go, but they're extremely limited. So you almost rarely use them. Slices are like arrays, but they're a little bit more like references. And this makes them both faster because you don't have to copy all the memory, but also a little bit, and they're also more flexible, but they're also have their own issues. They use arrays for backing storage. Arrays are actually a lot faster than linked lists. That's why they do it. And you can make slices of arrays. You can make slices of slices. And then you can use the range keyword if you want fast iteration of your arrays and slices. If you have any unused variables, you can use the blank identifier to assign to them. And then that way Go won't whine at you. But you have to be careful about modifying slices because you could be sharing backing storage with other slices. So in order to be sure that you have new backing storage, so if you want to have a new copy, you need to initialize a new slice and then copy the original slice to it. So anyway, that's an overview of arrays and slices in Go. I hope you enjoyed this lesson, and I'll see you next time.